Okay, so we're just going to now put it all together. Once again, just kind of walking through with SPSS. We're setting our dependent variable. That's what we're predicting, why. We're now looking forward to actually creating blocks. So in this example, you'll see that I have put 3 variables, depression, anxiety, and sex, into the model. And I've chosen a method at this point, enter method, to actually have within that block what order that I'm going to let SPSS decide to put those in. At this point, I do want to actually set the linear regression statistics. I want to tell it that I do want the estimates of the coefficients. That's going to give me that t information. That's going to let me know within individual models whether a predictor is significant. It's also going to give me that constant information and that b-weight information that I need to actually do prediction. I want to tell it that I want model fit. I want R-squared change. I want the descriptive statistics. And because we don't like to calculate things by hand, I also want both the part and the partial correlations. So at this point, I can go ahead and then enter a second block, and in this case, that's what I'm doing now. So I've come back, I've hit next block, which causes me to get to block 2 of 2. And in this case, I'm putting depression squared and anxiety squared in. So these are variables I've created to look for nonlinear trends. And again, I've currently just let the default stay standard with the enter method as how it's going to actually interpret these two nonlinear relationships, what order that the program is going to put them in. And finally, I'm going to put a third block in, and this is depression by sex. So this is again a created variable where I multiplied every individual person's score on depression by their score on sex to create an interaction variable. And again, it's set to enter. In this case, it doesn't matter though because there's only one predictor in the model. So we run it, we get SPSS, and again, we're going to see we've got Model 1, Model 2, and Model 3. So Model 1 is predictors of the constant, sex, anxiety, and depression. Model 2 is the predictors with both sex, anxiety, and depression still in the model, but we've added the nonlinear terms for anxiety and depression. And finally, Model C, again, has all of those and has added the interaction. So we notice the very first model is significant. It has a significant F of 0.001. The second model is not significant. The third model is not significant. So that tells us there's no nonlinear terms that explain variance above and beyond the linear terms in the first model, and that there's not an interaction worth noting beyond what's already explained by that first model. Which means on the second chart, I'm only going to be interested in Model 1 because that's the one that was significant. And again, I'm going to take a look to see what is that significance. I'm going to find that F value, 7.367, with a significance of 0.001. Now I want to look at those regression coefficients for that model. And again, I'm not looking at Model 2 or 3 because those models weren't significant. They didn't add to the prediction. And again, what I'm interested in is what are the significant predictors. And taking a look, we'll find that depression is not a significant predictor. However, anxiety and sex both are. And we're also going to get the correlations, both the partial correlation and the part correlation. So again, remember what those two different things are. That again, the partial correlation versus the part correlation and what it's explaining as far as variance is concerned. So, wrapping up here, what we've now done through this class is we've talked about descriptive statistics, means, standard deviations, and also how to determine if we have normal distributions, and to also look for outliers and other problems such as skewness and kurtosis. We've talked about z-tests and t-tests for single samples, so basically situations where we have a single measurement, a single continuous variable, but we're wanting to compare it to a known value. We've also talked about the two types of t-tests. So t-tests again are when we have a dichotomous categorical variable, which is our IV, and a continuous outcome. And really the difference here is that with between subjects tests, group 1 and group 2, condition 1, condition 2, whatever our independent variable, our dichotomous variable represents, are different subjects. Within subjects t-test, we basically have a situation where the people that are in the study were exposed to one condition and then the second condition. So it's the same people in both conditions, and that's the within subjects t-test. We talked about basic correlation, what we can do with it, that we can do bivariate correlations, and bivariate correlations means we have two continuous variables, that we can do point biserial correlations, A point by serial correlation means one of those variables is a dichotomous categorical variable with two levels, and then a continuous variable. And finally, we can do Spearman correlations if we have non-standardly distributed data, or we're needing to do conversions for other reasons, or we have ordinal data. We talked about simple regression, basically only taking a correlation and now adding a predictive element in that prediction equation. And finally, we've gotten the multiple regression out of the way. As I've referred to it, the kitchen sink of statistical techniques. So we can also add that one to our toolkit. Except, as I kind of indicated, actually, multiple regression has a lot of uses. It's one of our workhorses of statistics, and we're not really done with it. We're just done with it for the moment, because there's a lot more to it, and there's a lot more we can do with it, and we're going to come back to that when we end up into next semester talking about more advanced statistical techniques, most of which are expansions or, in fact, increased abilities of the multiple regression. So again, going back to our what statistics to use decision tree that we started the semester with, our first question of how many variables. If there's a single variable and it's continuous, that's t-test or z-test for independent samples. If there's more than two variables, we have to ask the question, is it continuous or categorical IVs? If it's a continuous IV and we have three or more variables, so 2 plus, that means it has to be multiple regression if we have continuous independent variables. If it's two levels, we have two variables, then we ask, is the DV categorical or not? If it's not categorical, we're at correlation or regression. However, assuming that the IV is categorical, we actually are going to then ask, is it got two levels? Then we're looking at simply the question of between or within subjects, which gets us to between t-test for independent or within t-test for dependent. So once again, if we have two variables, always assuming that the outcome, the DV, is continuous, then if it's a categorical variable, the independent variable, and only has two levels, that means we're using a t-test. So we've basically covered all of this at this point. We've covered the situation when we only have a single variable, a continuous outcome. We've talked about situations where we have more than two variables, however, at least one of those variables is a continuous variable beyond the outcome, that's multiple regression. That if we have only two variables, one IV and one DV, but the IV is continuous, that's correlation or regression. And finally, what we're now going to be moving to is that final part of the equation, what if we have a categorical IV that has more than two levels?